The determinant is defined just for square matrices, as we said several times in the previous lectures. Whereas the rank of matrices is defined for an arbitrary matrix. It doesn't necessarily require the assumption for the matrices to be square. As we can see, we can still use the concept of the determinant, but in a more subtle way. We made clear several times that the determinant is defined only for square matrices. There is no definition of determinant for rectangular matrices. However, it is possible to use the concept of determinant to get information about any matrix. The definition of a submatrix. So let A be any matrix. So a submatrix of A is a matrix obtained by removing some rows and some columns from A, just as one would suspect. So it is a matrix that somehow is contained in A, and the description is by removing columns and rows of A. A minor of order k of a matrix A is the determinant of a square submatrix of A of order k. We stress the fact that the minor, according to this definition, a minor is a real number because it is the determinant of some submatrix. It's not the submatrix, but it is its determinant of course, a square submatrix, otherwise we would not be able to talk about determinant. And, well, we introduce the order of the minor according to the order of the submatrix. Let's see an example of a minor of order k. Consider the matrix written here. A square submatrix of order 2 can be taken to be the following. B, a 2 by 2 matrix, of course, because we are talking about a submatrix of order 2, so whose determinant is a minor of order 2. It is 3, negative 1, 0, negative 1. The rows are the following. How do we get that from this matrix? Well, you can see from here, if we delete the second and the fourth, and we delete the second row, what remains is just a 2 by 2 matrix, precisely named B. Well, its associated minor is determinant of B is negative 3. So a minor of order 2 is negative 3. A minor of order 2 of the matrix A is negative 3, because negative 3 is the determinant of this order 2 square submatrix of A. We now state the theorem that links the concept of minors of a matrix A to the rank of the same matrix. Let A be any matrix, then the rank of A equals the largest order of non-zero minors of A. As you can see, the concept of determinant is playing a role through the definition of minor. We are basically not looking at the determinant of A, but we are looking at the determinant of submatrices of A, square submatrices of A. So A can be non-square, but certainly we will be able to find some square submatrix of A. Then we can define the concept of minor of A, and the link between minors of A and the rank of A is exactly as stated in the theorem. Consider the matrix A written above, this one. It is a 3 by 4 matrix, 3 rows and 4 columns. Therefore, by definition of row rank or column rank, the rank of A will certainly be less or equal than 3. So the minimum between the number of rows and number of columns. So 3. Now we have seen that the matrix B, it is a submatrix of A, and its determinant is different from 0. Therefore, by the theorem, we have that the rank of A is greater or equal than 2. So remember, here is written the rank of A equals the largest order of non-zero minors of A. So since here we are able to present a minor of order 2 that is non-zero, namely the determinant of B, certainly the rank will be greater or equal than 2. Therefore, there are two possibilities. One is that there exists a non-zero minor of order 3 of A, or else the opposite. So all the order 3 square submatrices of A have determinant equal to 0. Hence, there is no minor of order 3 that is non-zero. Here is the matrix A. So let's see which one of the two is true. It is true A, the possibility A, or the possibility B. We'll have to analyze the rows. Actually, it is better to analyze the columns and see how many of them I can find that are linearly independent. In A, there are 4 order 3 square submatrices. I obtained them just deleting alternatively one of the columns. However, we do not need to check the determinant of all of them. By the theorem or by looking at them, we have that the column 3, 1, 0 and negative 1, 2, negative 1, that are the first and the third column, they are linearly independent because, well, simply they are not one multiple of the other. Therefore, we just need to check whether one of the remaining column vectors is linearly independent with these two. The remaining ones are the second column vector and the fourth column vector of the matrix. If one of the two is linearly independent with these, the first and the third, then considering these 3 column vectors, I will have an order 3 submatrix whose determinant is non-zero because they are 3 linearly independent vectors. The column are 3 linearly independent vectors, therefore the determinant is non-zero. Otherwise, if both of them, both the second and the fourth column vector are linearly dependent, so they are linearly combination of the first and the third vector, then the rank of the matrix will be 2. Let's check, for example, the first 3 column vectors. So 3, 1, 0, 0, 2, negative 1, negative 1, 2, negative 1. We are checking whether the second column is linearly dependent with the first and the third column. Okay, this will be decided by the result of the computation of the determinant of this submatrix. If it will be non-zero, then they will be all the columns will be linearly independent, and if it is 0, then they will be linearly dependent, which means, by what we have just said, that the second column will be a linear combination of the first and the third. So expanding the determinant, we see that it equals 1. So we have a minor of order 3 of the matrix that is non-zero. Well, therefore, we conclude that necessarily the rank of A is going to be equal to 3, because cannot be more than 3, and because it has 3 rows. And but it does have a minor that is non-zero of order 3. Therefore, the rank of A is 3 by the theorem that we just stated.